Let a function f be continuous and positive for all values of x in a closed interval from a to b, which basically means that the curve should be smooth, without gaps, and above the x-axis in the closed interval. Also, let a of x represent the area of the region between the graph of f and the x-axis from the lower endpoint a to an arbitrary point x for every point x in that closed interval. Then, the derivative of the area function is equal to f at every point in the closed interval. As an example, let's calculate the area between the graph of g of x equals x cubed and the x-axis from x equals 1 to x equals 2. X cubed is continuous and positive for all x values greater than 0. In particular, it is positive in the closed interval from x equals 1 to 2. If the derivative of a of x with respect to x is equal to x cubed, then taking the antiderivative of the derivative of a of x, which is a of x, will be equal to the antiderivative of x cubed, or x to the fourth over 4 plus a constant, applying the power rule for all x in the closed interval from x equals 1 to 2. By definition, a of 1 represents the area between x cubed and the x-axis at x equals 1. Since the width of a line is 0, the area under the curve at that line is 0. Substituting 1 for x in the expression for a of x, we get 1/4 plus c equals 0, or c equal to negative 1/4. So a of x is now x to the fourth over 4 minus 1/4 for all x between x equals 1 and 2 inclusive. To the right endpoint, we have a of 2 equal to 3 3/4. So the area between the graph of x cubed and the x-axis from x equals 1 to 2 is 3 3/4 square units. Now, let's use this theorem to find the area between two curves that satisfy the hypotheses in a closed interval. If f and g are both continuous and positive functions, and the values of f are greater than those of g at every point of a closed interval from a to b, then the area bounded by the graphs of f and g between x equals a and x equals b can be found by subtracting the area between the graph of g and the x-axis from the area between the graph of f and the x-axis. Let's find the area between f of x equals 4 minus x squared and g of x equals x cubed between x equals 1 and 2. Sketching the graphs, we can see that the graph of f is above or has values greater than those of the graph of g from x equals 1 to their point of intersection. And from the intersection point to x equals 2, the reverse is the case. We can find the value of that point of intersection by setting the two functions equal to each other and solving for the x values. There is one real solution at approximately x equals 1.3 and a pair of complex conjugate solutions. Let's digress for a few moments to see how to get that real solution. This method is based on the work of mathematicians from the 15th and 16th centuries. Once one root is found, the other two can be found by easier methods such as division and the quadratic formula. Calculating the approximate area between f and the x-axis from x equals 1 to the point of intersection, as a polynomial function, f is continuous at every value of x and has positive values between x equals 1 and 2. The derivative of f's area function can only be equal to f if that area function is equal to 4x minus x cubed over 3 plus a constant for all values between 1 and x. The area between f and the x-axis at the left endpoint is 0, so a sub f of 1 is equal to 0, which is 4 minus a third plus c, which gives us c equal to negative 11 over 3, and the area function equal to 4x minus x cubed over 3 minus 11 over 3. Up to the right endpoint, the point of intersection of the two curves, the area between the graph of f and the x-axis is approximately 4 times 1.3 minus 1.3 cubed over 3 minus 11 over 3, which comes to about 0.8 square units. We calculated the area function for g with x equals 1 as the left endpoint earlier, and got a sub g of x equal to x to the fourth over 4 minus 1/4. The area between the graph of g and the x-axis from x equals 1 to the intersection point is then approximately 1.3 to the fourth over 4 minus a quarter, which is approximately 0.46 square units. So the approximate area between the curves from x equals 1 to the point of intersection of the two curves, subtracting the orange region from the light blue region, leaving the green region, is 0.8 square units minus 0.46 square units, or 0.34 square units. In the closed interval from the point of intersection of the graphs of f and g to x equals 2, the graph of g is above the graph of f. At the intersection point, the area between the graph of g and the x-axis is 0, so the constant of integration for g's area function will have a value of negative 0.71, and the area function itself will be x to the fourth over 4 minus 0.71. From the point of intersection to x equals 2, the area between the graph of g and the x-axis is approximately 2 to the fourth over 4 minus 0.71, or 4 minus 0.71, which comes to 3.29 square units. The area between f and the x-axis at the intersection point is also 0, so the constant of integration for f's area function will have a value of about negative 4.47, and f's area function will then be 4x minus x cubed over 3 minus 4.47. From the point of intersection to x equals 2, the area between the graph of f and the x-axis is approximately 8 minus 2 to the third over 3 minus 4.47, or 8 minus 8 over 3 minus 4.47, which comes to about 0.86 square units. The area between the graphs of f and g from their point of intersection to x equals 2 is then approximately 3.29 minus 0.86 square units, or 2.43 square units. The approximate total area between the graphs of f and g between x equals 1 and x equals 2 is the sum of the areas of the two green regions, or 0.34 square units plus 2.43 square units, which is 2.77 square units.